In the distant outskirts of our solar system, beyond the orbit of Neptune, ancient worlds lie cloaked in darkness. Pluto, long believed to be just a frozen, lifeless rock, revealed towering ice volcanoes and a mysterious sky that slowly fades into the void. Nearby drifts a smaller object named Arrokoth, a reddish relic shaped like a flattened snowman, preserving clues to the birth of planets. What secrets lie beneath Pluto's icy crust? How did such an unusual form emerge under the gentle pull of cosmic forces? And could life possibly exist in Pluto's hidden ocean? In this journey, we uncover the latest discoveries about Pluto and Arrokoth, two distant mysteries at the edge of our solar system. New Horizons passed Pluto in July of 2015. It shattered our assumptions about this distant dwarf planet. Instead of a frozen, inert ball, Pluto greeted us with a surprisingly complex and youthful landscape. One of the most astonishing discoveries was a network of giant ice volcanoes, or cryovolcanoes, unlike anything else in the solar system. Later in March of 2022, a more detailed analysis of the data revealed that in the planet's southwestern quadrant, at the edge of the heart-shaped bright region, there are massive dome-shaped mountains with a textured, lumpy surface. One of them, Right Mons, rises about 3 miles high and spans 90 miles across, comparable in volume to Hawaii's Mahunio volcano on Earth. The nearby Peart Mons is another colossal dome. These are not fiery volcanoes, but icy ones. If they erupted, it would not be molten rock, but a slushy mix of water, ice, methane, and other volatile substances oozing out like a semi-frozen glacier. What makes Pluto's cryovolcanoes truly intriguing is their apparent young age. The area around them is nearly free of impact craters, suggesting that the cryovolcanoes formed in the geologically recent past. They may be only a few 100 million years old or even younger, just a blink of an eye on a cosmic timescale. Some scientists believe the region might still be active today, slowly reshaping itself as the semi-frozen lava seeps from the planet's interior. Such recent activity is puzzling. Pluto is small, only 2/3 the width of our moon, and far from the sun, so you might expect its internal heat to have faded away long ago. Yet the existence of these enormous icy volcanoes implies that the planet has somehow retained enough energy to support geological processes late into its lifetime. This forces scientists to rethink how dwarf planets function and raises an exciting question. What source of heat still stirs Pluto's insides? Some suggest the heat is released from a reservoir of radioactive elements in Pluto's rocky core. Others point to possible antifreeze components deep inside the planet, substances like ammonia that lower the freezing point of water and keep it liquid and warm. Whatever the source, Pluto's cryovolcanoes stand as frozen proof that this distant world is not so dead after all. During the flyby, New Horizons observed giant cracks and depressions on Pluto's surface, tectonic features that reveal internal changes. It appears that Pluto's ice-water crust was stretched and pulled apart by forces rising from below. Scientists interpret these vast cracks and rifts as signs that a subsurface ocean is slowly freezing. As strange as it sounds, Pluto may host a subsurface liquid water ocean lying dozens or even hundreds of miles beneath its frozen surface. When water turns to ice, it expands, just like a bottle of water bursting in the freezer. The gradual freezing of a buried ocean could push the surface outward, cracking the crust. Indeed, images show that Pluto's crust has been stretched and broken over time. But there's no evidence that this underground ocean has ever frozen completely. If it had, the water would have formed a dense phase of ice under high pressure, so-called ice 2, which actually shrinks in volume. And this would have left telltale signs of a global compression, such as parts of the crust sagging inward. New Horizons found no signs of such activity. The lack of any sign of this activity leads us to speculate that liquid water is still there below Pluto's crust, says Dr. Alan Stern, New Horizons' principal investigator. But how could liquid water persist deep inside this distant planet where surface temperatures hover around minus 382 degrees Fahrenheit? Scientists believe Pluto's mantle retained heat from its formation and that insulation plays a key role. A recent study suggests a layer of gas hydrates, which is essentially ice mixed with gases like methane, could line the bottom of Pluto's icy shell, acting as an insulating blanket. These methane-rich clothrate ices have extremely low thermal conductivity, slowing the escape of heat and preventing the ocean beneath from freezing. In addition, ammonia in Pluto's water acts as an antifreeze, keeping the brine liquid at sub-zero temperatures.
All of this suggests that Pluto is an ocean world, albeit one locked beneath a thick crust of ice. This concept puts Pluto in the same league as Europa, Enceladus, and other ocean-bearing moons, except that Pluto's ocean exists without a giant planet nearby to flex and heat it. Research from 2020 even proposed that Pluto may have formed the hot way. Intense impacts may have rapidly generated enough energy to melt internal ice and create a liquid ocean from the very beginning. If so, Pluto could have had an ocean for over 4 billion years. A stunning idea that hints this remote dwarf planet might be more dynamic and even more potentially habitable than anyone ever imagined. Meanwhile, just above Pluto's surface stretches a tenuous veil of atmosphere, a ghostly blue haze made of nitrogen with traces of methane. This atmosphere, transient and thin, was another surprise from New Horizons, which captured the halo of blue haze illuminated during Pluto's sunrises and sunsets. For some time, Pluto's atmosphere was inflating. When the dwarf planet approached its closest distance to the Sun around 1989, its frozen gases warmed and sublimated, increasing atmospheric pressure. Earth-based observations showed that from 1988 to 2016, atmospheric pressure on Pluto roughly tripled as more nitrogen entered the sky. But now Pluto is moving away from the Sun on its 248-year orbit, and the trend has reversed. In 2019, astronomers observing a stellar occultation, the passage of the planet in front of a distant star, made a striking measurement. Pluto's atmospheric pressure had dropped by more than 20% since 2016. Another occultation analysis conducted in 2018 confirmed that the atmosphere is indeed thinning. Pluto's gaseous nitrogen is beginning to freeze and fall to the surface as frost. If current models are correct, this marks the beginning of Pluto's atmospheric collapse. Dr. Andrew Kuhl and his colleagues, who track the planet's seasons via stellar occultations, predict that by the 2030s, Pluto's atmosphere could almost entirely frost out, condensing into surface ice. During the long, cold winter, especially in the years after 2030, when the northern hemisphere is in darkness, temperatures will drop so low that the remaining gas will stick to the surface as thick deposits of nitrogen and methane ice. For several decades, the planet may become an airless, icy ball. Its sky clear, except for fleeting traces of vapor near sunlit regions. The cycle is not a permanent doom. Later in its orbit, when the southern pole eventually tilts toward the Sun several centuries from now, the atmosphere should puff up again as the ice sublimates once more. But for now, we're witnessing a rare planetary event, the compression and possible temporary collapse of an atmosphere in real time. As the pressure drops, the beautiful layers of blue haze observed by New Horizons will disappear. Interestingly, Pluto's overall brightness might even increase slightly as more of its surface becomes coated with fresh reflective frost. It's also remarkable that in 2015, while flying over Pluto's equatorial region, New Horizons spotted something completely unexpected: dunes. Yes, dunes, similar to windblown sand dunes on Earth. They're located at the boundary between Pluto's vast icy plain and its bordering mountains. These features were confirmed in a 2018 study led by Dr. Matt Teller. The dune-like ridges appear within a 46-mile-wide zone on the western edge of Sputnik Planitia, the large, heart-shaped nitrogen ice plain on Pluto, just where the ice plain meets the towering 3-mile-high mountains of water ice known as the Aldrisi Montes. They form parallel ridges of raised terrain that visually resemble wind-formed sand dunes, except here the sand is made of frozen methane grains. But how can dunes form in such a thin atmosphere? Surface pressure on Pluto is just 1 pascal, about 100,000 times thinner than Earth's atmosphere. According to common scientific belief, such a thin atmosphere shouldn't be able to lift or move sand grains. But Pluto found a way. During Pluto's solar day, solid nitrogen ice on Sputnik Planitia can sublimate directly into gas, releasing energy in the process. As this gaseous nitrogen expands and rises, it can briefly carry fine particles into the air. Dr. Teller and his colleagues showed that if methane ice grains just a few hundred microns across are lofted by this sublimation, the planet's faint winds, possibly blowing at about 22 miles per hour, are strong enough to transport the particles and collect them into dunes. These wind-blown grains are likely frozen methane originating in nearby mountains where methane ice caps exist, although some nitrogen ice fragments may also be present. And because the surface of Sputnik Planitia is geologically young, continuously refreshed by flowing nitrogen glaciers, the dunes themselves are likely relatively young, possibly formed within the last 500,000 years.
The discovery of dunes on Pluto highlights the surprising dynamism of this distant world. A thin atmosphere doesn't mean inactivity. Mars, with an atmosphere also thin by Earth standards, has carbon dioxide dunes. Even Saturn's moon Titan has dunes made of hydrocarbon sands. Now Pluto joins this club, proving that planetary winds can shape the surface even under the low-pressure, extreme cold conditions of the Kuiper Belt. After leaving Pluto, New Horizons set course for an even distant target, 486958 Arrokoth, formerly known as Ultima Thule. On January 1, 2019, the spacecraft flew past this tiny world at a distance of about 4.1 billion miles from the Sun, giving humanity its first close-up look at a primordial Kuiper Belt object. New Horizons found an object resembling a cosmic snowman, 2 irregular lobes neatly stuck together. The body is about 22 miles in length, with one lobe around 13 miles across and the other about 9 miles. It's a contact binary, formed from the merger of 2 separate bodies. Images taken during the encounter show a surprisingly smooth surface, a uniform reddish hue, and very few craters. In many ways, Arrokoth appears to be the most pristine and ancient object ever visited, a time capsule from the dawn of the solar system. One of the most striking surface features is the presence of large, mound-like segments that make up much of a larger lobe. A new analysis of high-resolution images revealed that the larger lobe, nicknamed Wenu, is covered by roughly a dozen broad mounds, each about 3 miles across. These mounds are remarkably similar in shape, size, color, and reflectivity. Arrokoth almost looks like a raspberry made of little subunits, notes New Horizons researcher Will Grundy. A smaller lobe, named Weo, may also contain a few of these mounds. Amazingly, the body is so well preserved that we can directly see the building blocks of its assembly.
These mosaic-like components suggest that it formed through an extremely gentle process. Scientists believe the mounds are locally formed fragments originating from the same initial cloud of material. They are not shattered pieces from violent collisions. Instead, they resemble siblings that grew together and gradually merged. There is a wealth of evidence supporting this view, based on the shape and chemical composition of Arakoth. Both lobes meet at a contact point, and their poles and equators are aligned, which suggests that the two objects once orbited each other and gradually spiraled together. The lobes themselves are flattened and somewhat pancake-shaped, which may be the result of a gentle merger within a rotating debris disk. Notably, the composition and color of the surface are strikingly uniform across both lobes. This indicates that the material from which this body formed likely originated from the same localized region of the solar nebula. If Arakoth had formed via the traditional method of hierarchical accretion, random collisions gathering material from different locations, we would expect a greater degree of heterogeneity. However, all signs point to a different formation mechanism, the cloud collapse model. In this scenario, a dense clump of solid particles in the primordial solar nebula collapsed under its own gravity directly into a planetesimal, skipping the stage of intense collisions. Study co-author Dr. William McKinnon explains that the particles of Arakoth formed close together at a low velocity, orbiting one another in an intricate gravitational dance before finally merging. All the evidence points to particle cloud collapse models and all but rule out hierarchical accretion for the formation of Arakoth. This discovery is a key piece in solving the long-standing mystery of the formation process of planetesimals, the building blocks of planets. Interestingly, the dim reddish tint of this body surface is not just a quirk. It tells a chemical story about the early solar system. Spectral measurements from New Horizons revealed that Arakoth's surface is coated with methanol ice and complex organic molecules, likely tholins. More on those in a moment. Remarkably, there was no trace of water ice detected on the surface. And this is surprising. Water ice is common among many outer solar system bodies. Even tiny comets and Kuiper Belt objects often show signs of water. Its absence suggests that either water is buried beneath a layer of organics, or the conditions under which this planetesimal formed resulted in an unusually low water content. Instead, Arakoth belongs to the class of ultra-red objects. Its reflectance spectrum is extremely red due to an abundance of surface organics. The reddish material is believed to be rich in tholins, which are complex macromolecules formed when cosmic rays and ultraviolet radiation interact with simpler compounds like methane, ammonia, and nitrogen. Tholins are not alive, but they are prebiotic. They include many of the chemical building blocks that, under the right conditions, can lead to the formation of amino acids and other ingredients of life. The presence of frozen methanol is another clue to this body's history. Methanol can form through the irradiation of water and carbon monoxide, or exist as a primordial ice. It is less volatile than gases like methane, ammonia, or hydrogen sulfide. Scientists believe that more volatile ices like methane, ammonia, and hydrogen sulfide might have once been present on young Arakoth. But gravity is so weak here and the surface so cold that over billions of years, these volatiles either escaped or chemically transformed. The detection of sulfur-rich tholins suggests that compounds like hydrogen sulfide were once present, contributing to the chemical makeup of the surface.
Once those gases either escaped or polymerized into solids, what remained was a reddish organic frost and methanol ice, a kind of organic varnish coating the surface. The near-total absence of water ice on the surface may indicate that it is buried beneath this organic mantle, or perhaps that in Arakoth's region of the solar nebula, it was so cold that water ice clumped into larger bodies, while this planetesimal formed mostly from carbon-rich ice and dust. In any case, its composition tells us that the raw materials for planet formation were diverse. Studying these materials up close gives us insight into the chemical environment of the outer solar system 4.5 billion years ago. These are the same materials that may have arrived on Earth via comets and asteroids, possibly contributing to the emergence of life's components. In essence, this lifeless body has preserved in deep freeze the organic chemistry of the sun's infancy, a chemical process that could represent a starter kit for the recipe of life. By the way, these discoveries inevitably raise this question: could life exist in Pluto's ocean? If Pluto has managed to preserve a liquid ocean for billions of years, it means there's a stable water environment, the quintessence of all living things as we know them. The ocean likely contains ammonia and salts, which not only act as antifreeze, but may also serve as nutrients. And the dwarf planet's core, if it provides thermal and chemical gradients, could offer energy sources, for example, hydrothermal vents on the ocean floor, like those on Earth's seabed. Of course, there's no evidence of life on Pluto. New Horizons wasn't equipped to search for biological signs, but the very existence of a subsurface sea in this distant sun-starved realm suggests that the planet may be more hospitable to life than scientists previously thought. According to one researcher, beneath Pluto's cold surface, any life, if it exists, would be shielded from harsh cosmic radiation and insulated from extreme temperature swings. Such organisms would most likely be microbial and chemotrophic, obtaining energy from chemical reactions in rocks and water. Although this is unlikely, the question remains open. Did microscopic life originate in this hidden ocean? Or could it still arise today? It's likely that we may not know until a future mission directly explores these deep, dark waters. The New Horizons mission gave us only brief glimpses, a few days of data on Pluto, just a few hours on Arrokoth, but those glimpses revolutionized our understanding. Years later, planetary scientists are still studying the data and making new discoveries. Yet many mysteries remain unresolved, or are only beginning to hint at answers. Did Pluto experience icy volcanic eruptions in the recent past, and is this activity ongoing? How exactly does the dwarf planet's climate shift as its atmosphere thins and replenishes? Is this subsurface ocean in contact with the rocky core, or is it sealed beneath a layer of hydrates? How thick is the ice shell? And could there be liquid pockets closer to the surface? Are all cold classical Kuiper Belt objects like this, or is Arrokoth an anomaly? Answering these questions will require new missions and innovative approaches. There's growing enthusiasm in the scientific community for returning to Pluto. For instance, NASA has funded initial research into an orbiter, not just a flyby, but a mission that would stay and study the planet and its moons over many years. The mission concept envisions a spacecraft arriving at Pluto, entering orbit, and mapping the dwarf planet in high resolution, tracking seasonal changes in its atmosphere, and possibly even deploying a lander or impactor to analyze surface composition up close. Since entering orbit is a complex task requiring significant deceleration, advanced propulsion methods are under consideration. These include highly efficient ion engines powered by nuclear generators, or even futuristic concepts like thermonuclear propulsion. One of these clever ideas is to use Pluto's largest moon, Charon, as a gravitational brake. Researchers have found that the orbiter could perform several gravity assists around Charon and slow down or even exit Pluto's orbit with minimal fuel use, enabling a tour of the system and then a departure toward other Kuiper Belt objects. According to one of the proposed mission plans, a spacecraft would remain in orbit for 2 Earth years, then use Charon's gravity to exit and continue on to at least one more Kuiper-Belt object, perhaps another cold classical object, and even fly by another dwarf planet. If realized, this ambitious plan would greatly expand New Horizons' legacy, transforming a brief reconnaissance mission into a long-term expedition. In the meantime, New Horizons itself is not yet finished. The probe has continued its journey beyond Earth, measuring conditions in the Kuiper Belt and the heliosphere, the bubble of space influenced by the solar wind. And it's looked back at distant planets, measured dust and charged particles, and searched for additional suitable flyby targets. NASA has extended the mission at least through the late 2020s, so New Horizons will likely continue to report on the conditions at the edge of the Sun's influence, perhaps even encountering the cosmic boundary where interstellar space begins. Pluto and Arrokoth have shown that the final frontier of our solar system is not a static frozen graveyard, but a region with active geology, evolving atmospheres, and preserved history. And as new missions are set in motion, we wait, not for distant dreams, but for the next discovery already starting to take form in the shadows of the unknown.